We want to construct medical nanobots that hunt down cancer cells in the bloodstream, and artificial intelligence that safely navigates the unpredictable physical world. To reach that level of sophistication, our instinct is to write a script for everything. We engineer from the top down, writing deterministic code that attempts to map out exactly how a system should behave in every conceivable scenario. We assume that total micromanagement is the only way to guarantee safety. If we just establish enough rigid rules and account for enough variables up front, we expect the system will execute its task perfectly. But that demand for absolute certainty makes these designs incredibly brittle. The moment one of these heavily scripted systems encounters a variable it lacks a specific line of code for, an unexpected shadow on the road, a rare chemical signature, it freezes or it fails catastrophically. Yet, inside your skull is a network with 86 billion neurons, making trillions of flawless connections, and it builds itself perfectly every single time, even within a wildly fluctuating biological environment. The brain pulls this off without a central engineer or a master blueprint mapping out where each wire should go. Biology relies on a completely different methodology to construct intelligent systems. If we're going to build technologies of the future, we must borrow its approach. During early development, the brain is a dense, shifting terrain of overlapping tissue. There are no tiny highways or signposts guiding a growing nerve cell to its final location. Instead, the tip of a growing neuron forms a structure called a growth cone. It extends microscopic, finger-like probes known as filopodia, which physically reach out and feel the surrounding chemistry. These filopodia are totally blind to the final shape of the brain. They're sent out into a chaotic environment and forced to fend for themselves. They act as autonomous agents, independent units executing local decisions based only on the immediate feedback they bump into. Because they lack a map, they rely on physical noise and trial and error, blindly probing their immediate surroundings in all directions to find the correct path. By randomly exploring, a filopodium adapts to minor physical shifts in the tissue, adjusting its course on the fly to hit its target with total accuracy. This kind of localized decision-making directly translates to information theory and the way we program basic algorithms. Evolutionary biologist Richard Dawkins noted that DNA does not contain a literal architectural drawing of the final organism. Instead, genes are like a baking recipe, a strict set of local instructions on how to mix the ingredients without showing a picture of the final cake. This cellular automaton illustrates the concept. Mindless black and white pixels follow basic rules, reacting only to their immediate neighbors. When you execute these local rules across thousands of autonomous agents, the interactions scale up into staggeringly complex, self-organizing patterns. The system adapts and generates highly organized macrostructures entirely on its own, rendering a central planner obsolete. For a traditional engineer, this is terrifying. When you unleash autonomous agents equipped with local rules, you forfeit the ability to predict the exact path the system will take. To understand why that loss of predictive control is effective, look at a professional soccer season. In any given 90-minute game, 22 players make individual choices, reacting to constant feedback. The exact outcome of a single pass, tackle, or shot is chaotic and impossible to forecast. This plot shows chaos scaling into order. Up close, individual points are frantic. Over 10 years in the German Premier League, macro statistics show exactly 46% of matches end in a home victory, with a 2% error margin. Relinquishing strict micromanagement over individual actions is the mathematical price you pay to guarantee global stability. Which brings us back to our ambitions. We want to deploy nanomachines into the bloodstream and let self-driving cars navigate city streets. You cannot have a system capable of adapting to an unknown environment while simultaneously demanding total, top-down control over its every move. We have to abandon the industrial mindset of rigidly assembling complex machines from static blueprints. Instead, we have to learn how to grow our technologies. We need to program robust local rules, unleash autonomous agents, and allow the network to self-organize in response to its environment. Surrendering control isn't a failure of engineering. It is the prerequisite for creating true intelligence.